At its core, a processor is a remarkably strict machine. It cannot read English, Python, or Java. It requires all information to be delivered as pure binary machine code. This creates an immediate physical constraint. There is a massive gap between the abstract logic that humans use to write software and the exact hardware instructions the processor is physically capable of executing. To manage the execution of this binary, the CPU relies on specific internal hardware. Components like the program counter keep track of the current sequence, while the accumulator handles active calculations. Understanding how a computer actually runs your software requires solving two separate problems: how we translate our code into something the hardware understands, and how the hardware manages unpredictable events without losing its place. Because a processor executes instructions in a strict linear sequence, bridging the gap between human ideas and hardware reality requires two completely distinct systems: translators and interrupt service routines. If we look closely at how humans program, the closest step to raw hardware control is a low-level programming language. The most common of these is assembly language. Instead of abstract concepts, assembly relies on mnemonics, short, alphanumeric codes that represent specific hardware actions. This snippet from the syllabus shows typical assembly code. You can see the mnemonics directly instructing the hardware. LDA loads a value into the accumulator, add performs arithmetic, and STO stores the result. But the processor still cannot read LDA or add. These mnemonics must be converted by a utility program called an assembler. This table illustrates the assembler's exact output. It translates the text instructions directly into the pure hexadecimal and binary machine code the processor demands. Notice the structural relationship here. One line of assembly code yields exactly one line of machine code. This one-to-one mapping produces incredibly fast, space-efficient software. However, writing an entire operating system or a 3D application, one hardware instruction at a time, is far too slow for modern development. We need higher-level languages. Languages like Python or Java allow developers to write complex, human-readable logic, but that complexity requires much more sophisticated translation methods. The first method is a compiler. A compiler takes the entire block of source code and parses it all at once, before the program ever runs. The output is a single, standalone executable object file. Because it processes everything as a single batch, a compiler requires the code to be completely valid. If there is a syntax error anywhere in the program, it generates a final error report and refuses to create the executable file. An interpreter takes a different approach. Instead of batching, it translates and executes the source code sequentially, line by line, during runtime. It never creates a standalone file. This means if an interpreter hits a syntax error on line 3, it will successfully run lines 1 and 2, but immediately halt execution the moment it encounters the flaw. This summary table explicitly outlines the exam criteria for these two tools. You must contrast the compiler's entire program translation and executable output against the interpreter's line-by-line execution. Ultimately, whether you compile your code in advance or interpret it on the fly, the final output is pure machine code, ready to be fed into the processor. The processor consumes this machine code using the Fetch-Decode-Execute cycle, repeating the sequence billions of times a second. This strictly linear loop presents a logical problem. If the processor is locked into executing a predetermined list of instructions, it has no way to react to sudden, asynchronous events. To solve this, the system relies on an interrupt. This is a specific signal sent from hardware or software to the processor, indicating that immediate attention is required. Hardware interrupts are physical events. If a printer runs out of paper or you press a key on your keyboard, the device signals the CPU. Software interrupts occur when a program generates a severe operational error, like attempting to divide by 0, or when two separate processes attempt to access the exact same memory location. As this flowchart of the FDE cycle shows, the CPU manages these signals by checking the interrupt queue strictly at the very end of the execute phase. By checking for interrupts only at this exact point, the processor ensures the current instruction finishes completely, preserving data integrity before pivoting to handle the new crisis. When an interrupt is detected, the processor must evaluate it. Interrupts are given priority levels. and the CPU will only break its current cycle if the incoming signal has a higher priority than the executing program. Let's track the exact mechanics of a valid interruption. Right now, the CPU is running standard software. The program counter holds the memory address 0010, directing the processor to its active task. To avoid losing its place, the CPU suspends the program and performs a state save. It pushes the data from the program counter and active registers into a specific memory structure called the stack, creating a secure stack frame. With the current process safely stored, the processor executes the interrupt service routine, or ISR. It updates the program counter to the address of the interrupt's code and processes the required logic. Once the ISR resolves the issue, the processor restores its state. The stored stack frame pops off the stack, flowing back into the registers and cleanly resetting the program counter to 0010. This strict choreography, pushing register data to the stack, executing the ISR, and popping the data back, is the invisible mechanism that allows a computer to seamlessly multitask. A processor is a highly constrained machine. Translators, whether assemblers, compilers, or interpreters, provide the mandatory bridge to convert human logic into the pure binary the hardware demands. Once that binary is in motion, the interrupt control system provides the flexibility required to break linear execution and react to a chaotic real-world environment. This matrix maps the complete execution environment. Source code feeds into translators, generating the required machine code outputs, which then enter the strict execution cycle, governed by stack frames and ISRs. To lock in these exact exam definitions, practice the specific paper questions, and review detailed mark schemes, visit www.studybuddy.tech. Computing often feels like magic to an end user, but by mastering the strict mechanics of translation and interruption, you understand exactly how the illusion is engineered.